Hello, I'm Cameron Smith, and today I'll be presenting my work on spatially selective passive acoustic mapping for improved monitoring of ultrasound-enhanced drug delivery. The aim of the work was to try and see if passive acoustic mapping could be used to monitor the efficacy of cavitation-enhanced antibody delivery in an in vivo setting. To find this out, we took CD1 nude mice, gave them HD29 tumors, and split them into 3 groups, each receiving an IV injection. The first received cetuximab, a therapeutic antibody. The second received this plus ultrasound and a low concentration of a cavitation nucleation agent known as sonotram particles, also known as nanocups. And the third group received the same but with a higher concentration of this cavitation nucleation agent. The experimental setup were 2 HIFU transducers, half megahertz, focused with an overlapping beam. Each of these has a rectangular cutout to allow for the placement of 2 L11-4 linear arrays. These allowed for the recording of the cavitation signals and also for B-mode imaging between each of the pulses. This allowed us to generate these sort of images while we were performing the treatments, where we could see where we were aiming, and we'd also be able to see, using PAM, where and how much cavitation was occurring. As for our results, what we found was that the mice who we had treated with ultrasound and cavitation had received higher levels of antibody in their tumors than ones that hadn't. And we also found that ones that had received a higher concentration of the cavitation agent also received a higher still level of antibody delivery. But these standard deviation bars are really large, so let's try and see what the PAM tells us. To do this, we had to use a metric such as the cavitation dose, where you integrate the PAM energy over the measured volume and normalize it by the tumor volume. This essentially creates an estimate for the average cavitation energy experienced by the tumor. And when we put this against the drug delivery, what we find is that the mice that had received higher levels of cavitation also receive higher levels of drug delivery. So it worked. But I wasn't completely happy when I found these results. I was curious as to why some mice, such as this mouse here, had received quite low levels of drug delivery, considering the fact that it had received quite a high cavitation dose. To try and find out why, I went back to looking at the original PAM videos that we had generated. And what was often found to be the case in mice that were anomalous were times like this, where cavitation occurred, yes, within the center of the tumor here, but also at times in the skin at the front of the tumor and also in the vascular bed behind the tumor. And so the question then became, okay, does the spatial distribution of this cavitation matter? Is it right to say that only cavitation that takes place within the tumor is improving the delivery of the drug to the tumor? To find that out, we created an automated algorithm that was able to take the B modes and create a binary mask to exclude cavitation occurring within the skin. And we also used a manual exclusion method to try and remove all cavitation that was occurring outside the center of the tumor. What we found was, this is what we had before, and when you exclude the cavitation occurring within the skin, we saw a minor improvement in the correlation. But when we removed all of the cavitation occurring outside of the tumor, we found a significant enhancement in the correlation between cavitation dose and drug delivery. So to conclude, PAM-derived total cavitation dose correlates with the drug delivery enhancement to tumors. This correlation can be enhanced further by excluding cavitation occurring outside of the tumor, and this shows that PAM can be used as a monitoring tool for the efficacy of cavitation-enhanced drug delivery. Thank you.